Okay, so good morning, everybody. This is my first talk today. It's a kind of a whiteboard PDF talk because it's something that is in progress. Yesterday I talked to Clee and some topics came out, so I will talk about something that I didn't plan actually, but I think it's interesting because it fits some arguments that we have been touching yesterday during our discussion. Okay, so the title essentially is the one that I wrote, is Super-Ehlers embedding in various dimensions. Essentially, I will focus on one particular case of these embeddings, which is the one that seemingly is relevant, for example, for arrays results, and actually, I guess it's interesting for everybody here. And essentially, I will refer to this paper, which dates back to 7 years ago. I wrote him with Sergio Ferrara and Mario Trigiante, actually when I was visiting Sergio at UCLA. And essentially, we studied this kind of embedding, which goes under the name of Super-Ehlers. I will explain why we are calling Super-Ehlers this kind of embeddings. Essentially, the observation that was made a long time ago by Ehlers is that gravity in d dimension enjoy an enhanced symmetry, which is SLD minus 2R. This is a split form, a non-compact real form of SUD minus 2. And this has a consequence at the level of the description of the graviton. So the degrees of freedom of a graviton in a d-dimensional Lorentzian space-time, of course we are considering some Lorentzian signatures, so one time and a certain number of space-like dimensions, the degrees of freedom are parameterized by this coset. And this coset, let me write here, this coset is quite important because essentially what happens is that this is described by a maximal and symmetric embedding where this algebra decomposes in this way, and in particular, let me see my notes, what's important is that so the decomposition of this algebra is such that SLD minus 2R is essentially decomposing as the adjoint of SOD minus 2, which is the antisymmetric plus the symmetric rank 2 with the unit determinant with the trace removed. And so this is essentially the graviton. These are the graviton degrees of freedom. And essentially, at the level of the algebra, we can write the coset algebra like this. So the generators of this coset are essentially given by this representation of SOD minus 2, and this is the graviton. So this is related to the Gerock. This is also related to the Gerock, in particular in 3 dimensions, where there is a further enhancement, and yeah, this is in some sense general because I'm not specifying the dimension D, where D is S plus T, and I'm considering S plus 1, so I'm considering a Lorentzian signature. Okay, so this is an observation that dates back a long time ago, and the new ingredient is supersymmetry and supergravity. Essentially what happens is that when you introduce these further symmetries, which in particular are graded Lie algebra symmetries, it turns out that you can have a further enhancement of symmetry. And in particular, this general embedding takes place where G is the enhanced symmetry in 3 dimensions. The upper script will denote the dimension I'm considering, and of a theory with a certain number n capital of local supersymmetries. So for the moment, just take this information. I will not be then talking about supersymmetry in particular, but in general there is this embedding, which might also be non-maximal and non-symmetric in general. And so you recognize here the d-dimensional Ehlers group. Why we dubbed these Super-Ehlers? Because these symmetries are electromagnetic duality symmetries and are essentially encoding the informations also concerning the local supersymmetry. So this is, even though this is a bosonic, it's all bosonic, but this bosonic is enhanced by local supersymmetries. And these embeddings are, have a number of features. Let me say that I will concentrate on M-theory. So in particular, if you want, the theory such that the low energy limit is described by the 11 supergravity. And so this will concern a certain non-compact form of E8, and also the symmetry SL9 will be relevant. Before specializing my analysis to the M-theory case, let me in general list some features of this kind of embedding. So the first thing is that this embedding is regular and in particular preserves the rank of the group, which means that the rank of G3n is equal to the sum of the rank of the two groups on the right hand side, and in particular these as rank d minus 3, so this is the general formula. In particular, this also holds for the non-compact rank. What is the non-compact rank? Well, simply we consider the Riemannian non-compact cosets related to this embedding, so we are modding each factor by the maximal compact subgroup. And so we obtain some cosets. They might be homogeneous or they might be symmetric or not, but still we have this expression for the rank of the corresponding cosets, or if you want, for the number of non-compact generators of each group. And a very important property, which will be relevant also for the discussion in M-theory, is that these cosets, which essentially are a consequence of, so let me write the embedding. So we have 3n, which contains, let me write at the level of the Lie groups. So we have gn d times SLD minus 2r. And of course, d is in general bigger or equal 3. And for d equal 3, of course, is trivial. We can write the corresponding coset and let me write the corresponding algebra of the coset. So is Gn3, this is the Lie algebra of G capital, and this is Gnd plus SLD minus 2r. So this coset is in general a pseudo-Riemannian coset, which means that there is a certain number of non-compact generators and a certain number of compact generators. And in general, all pseudo-Riemannian coset can be endowed with a character. The character is essentially the difference between the non-compact generators and the compact generators. And all these cosets, so the coset related to this embedding, to the Super-Ehlers embedding, so I will dub them Super-Ehlers cosets, have a feature that chi is vanishing, which means that the number of non-compact generators is equal to the number of compact generators. And this has a consequence at the level of the cohomology of the coset, because we will see that a certain operation, which is the Hodge duality, which essentially is Poincaré duality and electromagnetic duality, in this case, is an involution. And I will specify this better when I will talk about M theory. Okay, so I guess I can essentially switch to actually M theory. So I will be considering the case in which the number of supersymmetries in 3 dimensions is maximal. So I will consider maximal supergravity in 3 dimensions. And in particular, I will consider, I will start from G11. So essentially, what I will write is, can I save this, right?
At the top, you
this one?
Use like
yeah. Good. Okay. So essentially, what happens is that I will consider E88. This is a split form of E8. Is the split form of E8, and I will specify the previous embedding for D equal 11 and N equals 16. N equals 16 means maximal supergravity, maximal local SUSY. And D equal 11 means a signature which is ST equal 10,1, and this is M theory. So if you want, this is the Super-Ehlers embedding. I'm going to write the Super-Ehlers embedding for M theory. And the important thing is that if we specify D equal 11 and N equal 16, we know that there is no continuous symmetry in M theory. So essentially, the group is trivial. If you want, the algebra is void. So essentially what happens is that only the Ehlers group in 11 dimensions, so only the D equal 11 Ehlers symmetry will show up on the right-hand side of the embedding. And we know that D minus 2 is 9 in this case. And so we have this embedding.
So, so you are given essentially, you are embedding like a 3-dimensional manifold into 11 dimension?
I am embedding actually, yes, in the sense that the symmetry, the global isometry of the 3-dimensional, this is a 3-dimensional U-duality, or if you want electromagnetic duality symmetry, of a theory with 16 supercharges in 3 dimensions, so a maximal supersymmetry.
Or you can think of some sort of dimensional reduction from 11 to 3?
Exactly. And the point is that the symmetry, the Ehlers symmetry in 11 dimension is this one. Let me point out that in this case, this is a maximal embedding and is also non-symmetric, and so has this feature. And why this is interesting? Well, because as I said, we can consider this the generators of this coset. Okay, and what happens, what I will show in a minute, it turns out that the number of non-compact generators is equal to the number of compact generators and is equal to 84. And this 84 will turn out to be relevant and describe some particular gauge fields in this setting. So let me specify better this point.
About the M theory, you will say that this is the symmetry of some action that you call M theory?
The symmetry of the action actually is only bosonic in this case, and this is SL9. Actually, it's not really this, the symmetry of the action, but just only the maximal compact subgroup, which now you will realize is nothing but SO9. SO9 is the little group of massless objects, is the symmetry of massless objects in 10,1 dimensions. So essentially this will be the Well, it's not the symmetry of the Lagrangian, but is the so-called on-shell symmetry. So it's the symmetry of the equations of motion.
Is it possible to a fast idea of what is M-theory in this context?
Is it possible to give a very brief, simple overview of M
Yes.
theory?
Well, it will be a consequence. For the moment, just take it as mathematics, but then I will write the mathematics and I will tell you where the physics is of M-theory. So you will see in a moment what is M-theory. Well, actually, M-theory is rather, is the low energy limit, is the field theory limit of M-theory, which is n equal 1, d equal 11 supergravity, which is the unique... Still a mystery what actually is the real theory. Okay, so I will switch to another page, virtual page. And so let's now study once again the Super-Ehlers embedding. So for the moment, this is just the mathematical description of this embedding for d equal 11 and n equals 16. And so we have that the coset algebra, so the generators which give rise to the coset is given by this set of generators. And now let's study how these decompose. This is given by the adjoint representation of E88, and this essentially decomposes in the adjoint of SL9 and then into representations 84 and 84 prime, where 84 is the rank 3 form, and 84 prime is essentially the Hodge dual, or if you want, is the 6th form. I will be more explicit later. So this is the 6th form.
Remember that we were talking with, was it with Ray or Mike, that 84 is the number of zero divisors
Yeah.
of the Sedenians?
Yeah.
Anyway,
I don't know if there is
a
a-
coincidence. Anyway.
It's a coincidence for the moment. I don't know.
Yes,
It
yes.
would be
But please
interesting to
explain to them how do you get this number of 16 supersymmetries when you go from 11 to 3? Maybe that will help them understand how the n equals 16 when you have a spinor in 11.
Yeah,
and
essentially,
you
yes.
compose it in 3 dimensions.
So we start from n equal 1, d equal 10, 1 local supersymmetry. What does it mean? It means that there is, of course, a bosonic symmetry, which is the spin covering of the Lorentz group in 11 dimensions. But then there is also a generators of this graded symmetry, which is the supersymmetry. And these generators will actually be a spinor of spin 10, 1, which means the fundamental representation of the spin covering of the Lorentz group. And I will denote this with this psi in d equal 10, 1 and M theory, and n equal 1. And this is a real, it's a real spinor of dimension 32. So the dimension of this psi is 32.
The number of components.
The number of components of this spinor.
Like a column with 32 entries.
Yeah, exactly. And in passing, let me notice that this is not the only signature such that I can have a 32-dimensional real spinor. There are other exotic symmetries, exotic signatures such that one can actually have, but these are called the so-called M prime and them star theories, which have been studied, for example, by Crisal and all this stuff. Okay, so what happens? We are compactified then from 10, 1 dimensions. We are compactifying over a T8, an 8-dimensional torus, and essentially we end up with 2, 1, with a signature which is 2, 1, 2 space and 1 time. And of course, this representation of spin 10, 1 will break down because it's too big to be an irreducible representation of, in this case, spin 2, comma 1, which is the spin covering of a cell 2R. And what happens is that, so this spinner will become 16 times the spinner of 3 dimensions, of 3 Lorentzian dimensions.
The spinner in 3 dimensions has 2 components.
Yes, this is
so
2 dimensional.
A guy upstairs in 11 dimension had 32 components. So 32 divided by 2 is 16.
So this is the multiplicity of the generators of local supersymmetry in 3 Lorentzian dimensions.
So
okay?
That's
why the 16 is there. It's not really important for the moment, but yeah, I mean, this is just how the spinor generator decomposes. So let me study now, again, this coset. Let me write it again. So we have G of n equals 16, 3 over G of n equals 16, 11, and remember that this is void in this case, plus we have SL 9R, split form of A. This is the split form of A8. Okay, so let's study the coset, and this is E88. So we write down the coset. Okay, and so we study essentially the number of compact and non-compact generators of each of these algebras. And what we have is that the compact generators are 120, the non-compact 128, and SL 9R has 36 and 44. So let's compute the difference. So the signature of the coset will be given by 84, and 128 minus 44, 84. So you see that there is, as I anticipated, there is an equal number of compact and non-compact generators, and so the character of this coset, which is the number of non-compact minus compact, is 0. Now, the point is that these 84 fit in some representation, as I told you, of SL9, and 184, essentially the compact one, by if you want, by convention, is the 3 form of SL9, and the other 84, which is by convention the non-compact, is the conjugated, the dual representation, if you want, the 3 form prime, or if you want, the 6 form. Now I will be more explicit. Now, what happens is that, as I told to Marcello before, essentially physically what is important is the maximal compact subalgebra of SL9, which is SO9, or if you want, B4. And this is the little group, which means is the little algebra, which means essentially is the symmetry of the equations of motion for massless fields, which I'm specializing in this case. So I'm only talking of massless fields, actually, because the M theory, the field theory limit of M theory contains in this setting only massless fields. So let me just move to the next thing, and what is important is then that I will have once again this, and at the level of maximum compact subalgebra I will have SO16, which breaks down to SO9. So this is if you want, the numerator level, and this is the denominator level. Okay. And essentially what we have is that this gives rise to this coset. Let me write this way. And there is an analogous coset, which is SO16 times SO9. Now let's study the branching in these cases. So for the first level, let me write here, we have 248, which is equal to 80 plus 84 plus 84 prime. I already told you what they are, and I will now talk about physics, but let me just write down the second level. So the second level, this is 120, which decomposes in 36 plus 84. Okay. And so this is the decomposition, and let's try to describe what are the things that are here important. So the point, as I told you, we have a 3 form, we have a 6 form, and this 3 form is the so-called M2 brane, or better is the potential which couples to the M2 brane. So we have a 3 form potential coupling to a 2 brane, which is called M2 brane because it's a brane of M theory. And then we have, hi Mike, and then we have the 6 form which couples to the M5 brane. These are the 2 only possible massless branes in 11 dimensions, so in the field theory limit of M theory. As I told you, the fact that chi is equal 0 is such that essentially the degrees of freedom of the M2 brane are equal to the degrees of freedom of the M5 brane. Okay. So essentially this gives the bosonic content of M theory in terms of forms. Then, of course, in M theory I also have, there is also, of course, a metric, which is a symmetric traceless tensor. Where does it come from? Well, in this case we have another decomposition to be considered, the fact that SO16 is the maximal compass subalgebra. So let me just erase, for example, here, because I want all the fields to be on the same page, and I will study how E8 decomposes in SO16, in particular the split form such that this is a maximal compact subalgebra. When we do this, we have that 248 is given by still the adjoint of the SO16 plus the spinor. This is a chiral spinor in 16 dimensions. In this case, we have all Euclidean dimension, and this is a chiral spinor of dimension 128. And then we might study how this 120 decomposes now with respect to SO9. So we further decompose SO16 with respect to SO9. Remember that the SO9 is the symmetry of massless fields in M theory. And the nice thing is that this 120 decomposes as 36 plus 84, and then this 128, which is the chiral spinor, is essentially given by 44 plus 84 in terms of representation. What are these fields? These are the fields of M theory. You see that essentially you have the local symmetry. Of course, this is just this is 36, which is the adjoint of SO9, because it's 9 times 8 divided 2. So this is just the little group. Essentially, this disappears. But then 44, what is? 44 is essentially the degrees of freedom of a rank 2 symmetric tensor, which is traceless. So this is G mu nu. These are the degrees of freedom of a massless graviton, essentially of gravity in 11 dimensions. Then there are these other 84, which you can recognize to be nothing but the M2 and M5 brane. So you see that here, apart from, of course, the little algebra for massless fields, I have the graviton, the M2 and M5 branes. So these are the bosonic fields of M theory. Where is, where are the fermions? These are the bosons. Well, the fermions are given by, you know, this is, you see how mathematics fits perfectly with physics in this case. And let me just switch to this other page for fermions. So what are the fermions? So the fermions are given by, remember that E8 decomposes as 120 plus a certain spinor, but then one also has the conjugate spinor. Remember that in 16 dimension there is a chirality for the spinor bundle, so there is that the spinor bundle decomposes as psi plus psi prime or psi bar, and then psi bar, of course, will be 128 bar.
So of the gravitino now.
Yes, that's what I'm going to discover. So the fermions are essentially given by the gravitino, which is a vector tensor gamma 5 traceless, where alpha is, of course, is 32, and this is 4. So at the end of the day, you can compute the number of degrees of freedom, and it will turn out that you have 128.
You
And
know,
this
4 times 32
128
is 128. That's what he's saying.
Yeah. Yes, because the number of real degrees of freedom for the gravitino in 11 dimension is 128 bar. So this fits in SO16. Because SO16 is the so-called R symmetry of M theory.
This is where the cliff of 16 is so important.
Yeah, of course, SO16 is, if you want, one can determine the spin covering, and Clifford 16 will have a fundamental representation, which is the spinor representation.
This is why Tony likes it so much.
Yeah. So you see that in this way there is a precise correspondence between the Super-Ehlers embedding for M theory and the bosons and fermions of M theory. So all the degrees of freedom on shell of the theory are encoded in the mathematics of this embedding. Now, where is the interest, I guess, of this for you? Well, I was looking at the slides that Ray kindly shared with me, and in these slides, essentially, I recognized the fact that Ray was considering exactly the compact form, or if you want, the complex form of this decomposition, which is, of course, this is SL9. And he studied the commutators of the generators of representation of A8 and obtain various results. So I want now to show you how this comes from the mathematics of this coset. So essentially it's all encoded in this coset, and how I already showed you how the various degrees of freedom essentially have a direct meaning as massless fields in M theory. So essentially there is this physical meaning. That's why I think it's interesting for you. So
maybe you could explain to them the historical importance of E8, how this it was Kremer and Julia were able to discover this hidden symmetry, which was E8, that was associated with the compactifications of 11-dimensional supergravity to 3 dimensions. So it was a mystery how there was an E8 hidden somewhere. Related,
yeah, because
yes.
The point is that E8 is a global symmetry. But acts non-linearly on the scalar fields. So acts non-linearly on the scalar fields of 3-dimensional scalar fields of 3-dimensional supergravity. And a priori, this was not a symmetry that Kremer and Julia expected to exist when they studied the compactification of 11-dimensional supergravity, let me call it this way, is more correct, on a T8, and they studied the corresponding 3-dimensional
this is on the 8 torus. You compactify 11
this
dimensions
is the standard way.
on an 8-dimensional
the
torus.
Easiest way, yeah.
Yes, and then you end up with 3 dimensions.
And so essentially they noticed that there was a local symmetry which is SO16, So essentially, they only notice that there is this local isometry of the moduli fields, because when you compactify, you get some moduli. But these in supergravity are nothing but the scalar fields, are massless scalar fields. But then they realized that these scalar fields were acted upon non-linearly by a certain symmetry, and this certain symmetry was found to be E88 simply because there is a unique real Lie algebra such that SO16 is the maximal compact subalgebra, and this was found to be this. This was already known, of course, by mathematicians, but it's nice that there is a unique answer to the problem. Okay, so let me go back to the...
One last thing is that since David is here, you know, your advisor Sbibern for many years has been doing this n=8 supergravity, you know, 2-loop, 3-loop. So some people believe that it might be a finite theory of gravity in perturbation theory. And some people think that the real reason it might be finite is because there's hidden E8 symmetry. So this hidden E8 symmetry may be actually responsible for the magic cancellations of the, you know, of the right?
Yeah. Now they probably think it might you diverge around 7 loops in 4 dimensions, but it's still pretty good.
Yeah. Anyway, since David is here and he was your professor, anyway.
I have a question. So you said that Kremer and Julia were discovering the hidden E8 before Ed Wheaton wrote his paper on the heterotic.
Much earlier.
Before.
Much earlier.
Okay.
Yes, we are talking about this was
E8 is a French theory.
I think it's 1980 or 1981. I mean, the very first years of supergravity. Supergravity was introduced in 1976. So, I mean, just after 3 or 4 years, they discovered the maximal supergravity and so. Okay, so we have this 8-8 symmetry, which is global, but let me say that then there is this SL9R symmetry. And so I will essentially write down in terms of fields what? 80, 84, and 84 prime. These are representation of SL9R. And 80 can be written essentially as a field which has one index up and one index down, where let me say what I is going from 1 to 9, and this is in the 9, in the fundamental representation of SL9. Then we have J that goes from 1 to 9 again, but this is in the 9 prime, which is the contragradient representation of SL9. Okay? So we know that, of course, when we do 9 times 9 prime, there is a unique singlet, and this singlet is exactly the delta, it's ij. Okay, so this is nothing but the adjoint, so it describes the generators of this SL9. And then we have 84. As we said, 84 is the, if you want, in terms of Young tableau, this is this structure. And then we can essentially write this as Uijk, where this is completely antisymmetric. If you compute the number of degrees of freedom of a completely antisymmetric rank 3 tensor in 9 dimensions, you get 84. Now, this, as I said, is the 6th form, which means in terms of Young tableau, something like this. And this can be written, of course, once again as a completely antisymmetric rank 6 tensors. And how comes that they have the same number of degrees of freedom? Well, because, and this will be crucial in the subsequent analysis, there is a certain symmetry called Hodge symmetry or Hodge duality, which in this case is nothing but electromagnetic duality implemented on the cohomology of the manifold, and such that essentially I can define a star operation on the 3 form such that this is 1/6 prime. sorry, 6 factorial of epsilon A, B, C, I, J, K, L, M, N. This is the 9 index, rank 9 Ricci-Levi-Civita tensor. Levi-Civita, it's an Italian. In D equal 9 dimensions, and this is an invariant tensor, an invariant 9 form of SL9. And I will then compactify, I will contract with U, A, B, C, and then this gives me a 6 form, which I can write, if you want, as U, I, J, K, L, M, N. Okay.
This is just a property of the binomial coefficients in 9 dimensions,
yeah,
essentially.
Yeah. Okay, so let's study the commutators. Now, the commutators, we can already make some reasoning. I told you that this is a maximal non-symmetric embedding. And I will show you what non-symmetric means. Let's call this H. So essentially the set of generators of SL9, so this essentially is given by H. And let's call essentially this set of generators K. So what we have in general is that, let's call this G, so the algebra G. So we have a Cartan decomposition of E88 such that G is equal to H plus K. Okay. And let's study the commutators, but in an H covariant fashion. So let's study the commutators when we break G in this way. We can do that. And what happens is that, okay, we can study H with H, so the commutators inside this SL9 with themselves. Of course, what happens is that this will be inside H for the very subalgebra properties of H. This is Lie subalgebra. Then we can study the commutators of H with K, and this also in general will be inside K, simply because K, 84 plus 84 prime, is in this case, a reducible representation space for SL9. This means that this symmetry acts on K, but K is a representation space, so it's a linear representation space of H. It's nothing but this triviality. But then the important point is that let's study now the commutators, and these are interesting for results, of the 3 form and of the 6 form between themselves. So we can study K with K. And now the important thing is that in this case they will be in general contained in G. If the coset were a symmetric coset, essentially one might say that these were inside H, inside the stabilizer. But in this case, I will show you in a moment that they will actually have a non-vanishing projection on K, so in general, trivially, they are in G. This is essentially equivalent to say that the corresponding coset is a non-symmetric coset. And now I will derive exactly the same.
If it were a symmetric coset,
yeah,
the K with K will give you H?
Yes.
Okay, okay.
That's
okay.
the general. For example, there is a symmetric coset of this kind, which is similar to the one. This is essentially the moduli space of 3-dimensional supergravity, maximal supergravity. This is symmetric. So in this case, if I make the commutator of SO16 of the generator of this with themselves, they are inside K, so inside the adjoint of SO16, inside SO16. Okay, so let's go to the 8th page. So let's remember our fields. So we have A, Ij, then we have U, I, J, K, and then we have U, I, J, K, L, M, N. Okay. So as I told you, we have H, H, inside H, and this essentially means AB ij, and this is nothing but kbkj. So this is just a matrix multiplication. It's just the explicit form of the commutator. Okay, so this is trivial. It's essentially the algebra of SL9. Okay, then we have the other thing is that, as I told you, K is a representation of H. So what holds is that essentially we have A commuted with both U and U star. If you want, this can be written also as star U I, J, K, L, M, N. Okay, and what we have so is it's A, U, and this will have a projection of I, J, K. And of course, in this case, I, J, K is completely antisymmetric, but in the commutator, I will have to distribute these indices on A, which has only one index up. So what happens is that the explicit expression is something which probably, as far as I understand, is relevant for the Neo algebra, which is this one. You see that essentially what happens is that I'm distributing this index ijk, of course, one by one. Before we have I, then J, then K, and of course L, which is the contracted index, is moving in its position, is in first, in second, and in third position. So, sorry, this is U.
Is that your delta? Is that the delta, a Kronecker symbol somewhere?
Yeah, but the delta...
Your notation is... Okay, I'm sorry.
Yeah, the delta is essentially not given here. Essentially is the... If you want, when I do 9 times 9...
Yeah, is that singlet you were mentioning?
It's the singlet.
Okay,
so
okay.
This is 1
okay.
plus 80.
Okay.
And the 80 is this one.
Okay.
So the delta is it's not seen here. If you want, it's the generator of the C inside the GL9. If you want, of the R inside the GL9. Okay, and essentially you get something similar in the other case. Let me... Okay, so what we have is now that A must commute with U star. So the unique difference, I won't be writing, but essentially is the same structure with U star. You also have in...
Yes. When we have the 6 indices, it's more easy to use the 3 missing indices which are corresponding.
Yeah,
which is like computing the Hodge dual.
Yeah, I mean, it's the same thing.
They are different numbers, so, and the order doesn't count. So if you say 1, 2, 3, 4, 5, 6, it's the same as 7, 8, 9.
Yeah.
But the complement.
Yeah.
And then you can make the matching with 3, 4.
Yes. Let me show you at the level of representation what happens, because this is quite important. So essentially, as I told you, here we have 9. We have... Oh, okay. Can I get back? Okay. Okay. So essentially what we have is that H is 80. Remember, is 8 of SL9. And then we are considering a tensor product with 84. This is how things go at the level of representation. Now we have to study this. This is a general expression. It's given by huge representation. But let me say that when we project them, these are a huge representation of SL9, which, however, are not physical. And then you have to recognize, you have to project this representation on what? On G. And remember that G, which is E88, is decomposed as 80 plus 84 plus 84 bar, or prime, if you want. Okay? So you see that essentially when we project on G, we only have this, as it must be, because essentially this is K. So you see also from representation theory that this is satisfied, as it must be, because this is a coset. Now, the nice thing is about KK. As I told you, KK will be in G and not in H as a consequence of the non-symmetricity of the embedding. And this can, once again, simply be obtained by the representation theory of the algebras. And I think also this is related to the neo-algebra, right? To what you call the neo-algebra.
Which word do you use? Neo-algebra?
It's just the name that I gave, but I gave the table of commutator, which is the same
Yeah.
in the presentation.
And you give it the name N-E-U? N-U?
Neo, like in matrix neo, because there is.
Ah, nil!
Yeah, I will explain. Instead of using the indices I, J, K,
Yeah.
I'm using N, E, O. I can choose any one.
Ah, okay, okay.
One, Neo, Aeon, as ordered.
Okay, okay,
triplets.
okay.
So this is H plus K. Okay, so let's study this. Remember that K is equal to lambda 3 plus star lambda 3. Okay, so KK will decompose in a commutator of lambda 3 with lambda 3, and this essentially in terms of components is a commutator of U with V, and we'll have some indices I, J, K, and this is equal to 1 over 3 factorial times 3 factorial epsilon I, J, K, A, B, C, D, E, F, and then we have two of these tensor U, A, B, C, and V, D, F. So you see that it's antisymmetric, so it's a commutator between these two tensors, and we'll have some I, J, K indices low. So essentially this will belong to lambda 3 star. And on the other hand, then we can commute star lambda 3 with star lambda 3, and we will have a very similar expression. The only difference is that now the indices will be contragradient, will be up, but will be exactly the same, and this will belong to lambda 3. And finally, it's important to see what happens when we have lambda 3, so the M2 brane, which interacts with the M5 brane, if you want to make the interpretation at the level of massless fields of M theory. And this will be, at the level of components, will be U commuted with V star. And of course, this will have some components, some indices up and down, so contragradient and gradient. And this will essentially be given by 1/2 UIPQ with V star JPQ. But then there will be, Carlos, the delta appearing, because of course you remember that there is a projection over the adjoint, but then also the single generator, which is given by the invariant tensor, which is the Kronecker delta of SL9. And essentially this will be minus 1 over 18, these are normalization factors. Then essentially we have the contraction of U with V star. Let me write like this. I will be more explicit. And then delta Ij. The contraction is essentially this simple tensor product. Okay. You see that since they are completely antisymmetric, this is non-vanishing. Okay, so just by group theory, once again, one can deduce this. How? Well, once again, we can study 84, and this is crucial. You see that now this is given by some component in K, like this and like this. Where is it? I lost it. And this, because this belongs to K. Okay, and then there is a component instead of in H, which means that we cannot eliminate this. So this is essentially a non-symmetric embedding because has a non-vanishing projection over K. In particular, so this will be important. So we are making 84 times 84 bar. So this is a well-defined representation theory problem. Let's decompose these. Still, there are huge representations, but we don't care about them because these are unphysical. But mathematics tells you this. And then you see you have to project, you have to see which representation belonging to G are inside here. And once again, we recognize this and this. If you project over E8, we get 80 plus 1. So you see that it's consistent. Well, in particular, the plus 1 is not in G, so essentially it's only 80, of course. The plus 1, the removal of the plus 1 is given by this minus with the Kronecker delta. So everything is consistent. And you see that there is a precise matching between pure Lie algebra and the dictionary of massless gauge fields of M theory. So I think that this might be interesting because you might ask, how general is this? So we are essentially decomposing E8 in terms of fields of representation of A8. What happens is that not only one can do the same trick with all smaller exceptional algebras, so E7, E6, F4, G2. There are certain forms of AN such that allows for this decomposition. But if one goes infinite dimensional, so essentially continues the E series adding nodes to the Dinkin diagram of E8, so go to E9, E10, E11, and any hyper-Katz-Moody algebra, what happens is that, of course, this will become a set of infinite dimensional generators, so infinite generators, and one might say this is quite untractable. But then what happens is that, okay, this is true, but then we can make a sort of a series expansion of the set of generators with respect to one node, in particular to the spinor node, which is a certain node of the very extended Dinkin diagram. And what happens is that the first levels this is in one of Ray's slides. I mean, if you start making this series expansion, which is called level expansion for Katz-Moody algebra, you notice that essentially you can always make a decomposition, for example, of E9, which is this 9-dimensional. So E9 will have a decomposition starting with A9 and so on. I mean, you can always have AN inside the level decomposition of the hyper-Katz-Moody algebra with respect to the spinor roots. Of course, then there will be an infinite expansion, but the first terms are always given by the Lie algebra AN. And this, I think, is quite important also for the result that you have that essentially the E8 lattice is given by the A8 lattice 3 copies with a certain angle, which I mean, and because one can write down a series of conjectures for all the algebras. Let me get back to this. So essentially, what I discussed so far is E8 breaking to A8. And at the level of representation, this is 248, 80 plus 84 plus 84. And I showed you all the structure of this decomposition. There are other cases which one can consider. And essentially, let me see where they are. I did it here.
Alessio, did you talk to Ray about the idea of 4 copies of A9 compositing to the affine extension E9?
Not yet, but I guess that might be a possible guess to be explored. Now I'm just confining myself to the finite dimensional ones. But of course, one can warm up with the finite dimensional and then go in higher dimension. I want to see you that it's just a consequence of Lie algebra theory. So here, the result essentially is that A8 will be given essentially. let me write like this. There is a certain rotation of 1, and then the double of this rotation, something like that. Okay? So there are 3 copies. Of course, they are not. They are strongly overlapping, because if they were not, this would mean that this algebra is of rank 24. But of course, this is rank 8. But we have a certain overlapping of this.
They are not overlapping.
In the sense that the commutators are non-vanishing, of course.
Yes.
They must be non-vanishing.
Geometrically, the lattices are not overlapping.
Oh, yes, algebraically they are not overlapping because the commutator is 0. Of course, geometrically they are not overlapping in the sense that there are no coincident points in the lattice. Yes.
Each point of the E8 lattice belongs to one of the 3.
Absolutely, only one. Absolutely,
one,
yes. My overlap was algebraically. So of course the.
When you combine them together.
Yes, of course. Otherwise, E8 would be rank 24 if they would be commuting among themselves. So, and essentially, one can. I remember that we have been discussing this, and what happens is that. Let me write this. T of A4, A8. Sorry. Intersected with E8, of course I can take the positive root. This essentially is given by 84. Now, what about the others? I just tell you one other example, but what about other exceptionally algebras? Well, let me make just another example. And the example I'm gonna do essentially is it's again actually for E8, but because this is not unique, so it's not the unique way to get, of course, the E8 lattice. One may conjecture other ways, and one get inspired by Lie theory. For example, there is another possibility, which is we know that E8 contains A4 plus A4. This is a very nice embedding. Essentially, is SL5 plus SL5 inside E8. That's a maximal non-symmetric embedding, and the decomposition is such that so the 248 essentially decomposes in 24,1 plus 124. These are the 2 adjoint, and the other representations, which are the analog of the 3 form, and it's Poincaré dual. The other representation are exactly given by 10,5 plus 5,10 bar plus the complex conjugate. And what is 10? Of course, 5 is the fundamental of A4, and 10 is the 2 form. Sorry, the 2 form, not the 3, of A4. Simply because 5 times 4 divided by 2 is 10. Okay, so the conjecture will be that there will be, I would say, 4 pieces. So I would say that there are, the conjecture would be 4 copies of this lattice rotated by 1 angle and then multiplied by 3 times, for 3 times, might give rise to E8. This is a conjecture that might be checked, because these are quite simple lattice, I think, to be done. And as Klee was saying, the big deal will be then going to E9, and E9 is the affine algebra of E8. So essentially, the lattice of E9 is a layering of E8 lattices, such that each layer has an index, which is called level, and it will be interesting to see whether essentially E9 can be written as A9, a certain number of copies of A9. In order to see how many copies, one might get inspired once again by the, let me write E9 with respect to the spinor root, one of the two, and essentially this starts with A9 plus other generators. Essentially this A9 may also be written as A8, as the subalgebra A8 plus C plus other pieces. So I mean, by looking at the level expansion of E9 with respect to its spinor root, one might get inspired to conjecture how to construct E9 in terms of A9.
Yes, but we should use the affine extension of A8, not the A9. But
yes,
A9
of course.
is inside, but
you are right.
It's affine.
You are right.
A8,
I mean, what I mean
because
here.
for A it's not the same than for E. There is no
I was
ambiguity,
inspired. Okay, you are right. I mean,
A8
I was actually meaning this. So the affine extension of A8, not A9 in the sense of SL10. Absolutely.
So you have a whole building, layers and layers and layers of
So you see that
Yeah.
essentially we are reducing the problem to the much simpler problem of the affine extension of AN algebras.
And does that correspond to the geometric analog in terms of the A9 lattice?
Yes,
Okay.
exactly. A9, I mean A8 plus, the affine extension of A8.
Then obviously, yes, E9 is a 3A9 with this A9.
Yeah, so this might be
This is
important.
valid also.
How much time do I have left?
It was a 1 hour and a half.
So okay.
Alessio, did Ray ask three copies of A9?
I didn't ask.
He
I
states.
state.
So essentially, he's stating that it's possible to make this construction of E9 in terms of these three rotated copies
not
of.
necessarily four.
I guess three, right?
Three. Yeah.
Three.
You just take the same construction.
Because essentially, what happens is that
it has an infinite number of copies in the perpendicular dimension.
the affine extension goes really, if like I put a plus here, of course here we'll have the analog series of affine extension whose this is just the level 0. So I mean, one can
You have many
essentially-
floors. That's all.
I mean, you can, there are some decomposition, I mean, of E9 such that you get A8 and then you get all these other representations. So I guess that the number of copies of the A lattice stays 3. And then you get these structures.
And are they rotated or only translated?
Translate.
So then the
Yeah, I put T, of course. T is a translation.
so then the quantity of parallel vector classes in A9 must therefore be equal to the quantity of parallel vector classes in E9.
Yeah.
Because you
Yeah,
translate.
because these are translated. Yeah, it's a translation. Okay. And last observation, I want to just give you an explanation of the 0 character, which is quite nice. No, I want to keep this. So, why this E8 over SL9 has 0 character? So why chi? So the point is this: we can write this algebra essentially as lambda 3, the 3 form, the M2 brane plus the star of lambda 3. So this is M2 and then 5. These are the potentials which couple to M2 and then 5. And we have that the Hodge, this is the Hodge star, essentially associate a certain P to lambda D minus P, where D is the number of dimensions and P is the spatial extension of the brane, of the potential of the brane. And so you see that essentially this decomposition is such that if I apply star to this set, this is still this set, because it's commuting, for the very reason that this is the identity. So the consequence of the involutive nature of the Hodge duality on the cohomology of the coset is such that chi is equal to 0. And this, in principle, this is relevant also for the infinite coset. One might write down the infinite coset E9 over A8 plus. Let me be precise. So this algebra essentially will have a decomposition which will be Hodge, a cohomology which will be Hodge invariant, in the sense that the star in the study of the cohomology of this infinite dimensional coset will be an involution, such that the square is the identity. For the very reason that that construction of the affine extension of E8 in terms of these 3 copies of A9 understood as A8 plus is holding. So that's the last observation that I want to tell you.
And as a physics, so some physics interpretation, I think I read a long time ago that for string theories, the universe is M2 brane and M5 brane which are vibrating and intersecting, and so this intersection point of the 2 brane after vibration, maybe the point in our E8 lattice. If we say that maybe we have a discretized version of this brane,
we have
because
we
our
have
E8
because
lattice is the A8.
Yeah.
Which will more be the bosonic part, and the M2 and the M5 brane, which are spread all around this lattice.
Yes.
So it's logical that we can see them as a discretization of branes.
Yes, okay. So you are saying that essentially there is a one-to-one correspondence between the set of points of the E8 lattice, which correspond to the degrees of freedom of M2 and the M5.
And the 80 also, yes.
Of course, because then 80 is just the little group, I mean, it's the SL9, well, it's the non-compact enhancement of the little group, because the little group is before, and then we are A8. Yes, this is true. It would be nice to see, because of course now you are constructing E8 lattice as A8 plus the translation, I mean 2 other translated A8. Would be nice to see essentially how 84 and 84 prime, the degrees of freedom are scattered, are distributed in the points of these 2 other translated, if there is a one-to-one correspondence, or some of them are essentially have a non-vanishing projection on both sets of points of translated A8 lattice points. This I think can be checked explicitly.
Yes, there is a symmetry for each point in 84. The opposite point
I think
in the
that there
lattice
is
in 84 prime.
I was just guessing, but now you are
Yes.
confirming me, right?
Fang said something that I didn't see how it can be true. Better if you state the statement,
okay, so
make sure it's clear that it's geometric.
So the A9, you guys say the A9 is like kind of like the E9 is like a E8, like translated into the 9th dimension,
Yes,
right? But
dimension.
like imagine this is a this is a thin layer. I mean, this sheet is like a E8, and so to make it E9, you just keep on layering them up.
Yes.
But the distance between these different
one.
sheets, they're like a
Is one.
infinite. It has to be unit length.
Yes, so
Yes.
it's
yes.
one. It's not
An
one
integer,
half.
that going by
It's an
integers.
integer, yes.
Yeah.
the
Okay,
levels are
I thought the distance between them are also like infinite small or something.
No, it's a unit. It's like the floors of a building. They go by unit step.
Okay, so then come back to the question, and Clee's question, like E9 has the same vector classes, which is not true, because when you extend to the 9th dimension, and then so from point to point, there is another vector in the 9th dimension,
You have
at least.
Yeah, there is
vectors,
the level
yes.
vector. I mean,
Yeah.
We should be
apart
clear,
from the
because the way I phrased it before, we all agree.
Parallel
I'm
vectors,
not sure
huh?
how you. All I'm saying is that if you have n parallel vector classes in the A9 lattice, and then you simply take two copies, translate it without rotating, then you should have exactly n parallel
but
vector
you're
classes.
translating into the extra dimension.
No, I'm not.
No.
It's A9
There are two things.
translated in
No, but
nine.
it's I thought it's a
To what?
E8
No,
translating to
A9.
E9.
No, A9 translated.
Can you
Two
draw
copies.
it?
So let me draw. Let me
But
draw.
then they ask a different
Unless you're
question.
going to draw.
So
I
there
would
are two.
say like the
E9,
Yeah.
E8.
which is E8 plus, is something like this, where this is the so-called level. This belongs to Z. So we have 0, -1, 1, and so on. Okay. So of course, as a consequence of the fact that E9 can also be constructed as A8 plus 2 translated copies. So there are two things. So the number of parallel vector classes of A8 plus is equal to the number of parallel vector classes of E9, which doesn't mean that the number of course, parallel vector classes of E8 is the, of course, Fang is right because there is another vector in the perpendicular, but these are two different
It
states.
I have a
depends when you
simpler
say
question
parallel
that
vector
kind of
class,
bridges the
it's
gap.
not really well defined because it depends between which point you can accept to take edge that you integrate in your class.
Yes, I'm assuming, I mean,
You have to specify this.
the consequence is that, I mean, when you have translations, these do not modify in general the number of parallel vector classes.
No, but if you can join point from the first A8 plus to point from the second one, you
They're
can
not
generate
separate.
new edges, which
They're
are
not
not in the
separate.
first.
Yes, yeah, you are right. I mean, yeah, that's
I'm
another-
confused
You
about
have some
the relationship
inclusion, but
between
yeah.
A9 and this
Yeah, it's
A8
like you
plus.
use.
Hold on. Go ahead.
I'm confused about the relationship between A9 and this A8 plus because Klee is talking about A9 as the lattice, but this is an affine extension of A8.
No, we are talking about the lattice.
the lattice.
The A9.
yeah.
We're saying we can take 3 copies of A9 lattice and generate this.
A9 is the affine extension of A8. It's not SL10. It's not SL10. It's not a Lie lattice. I mean, it's a Kac-Moody. It's an affine extension of it. Yeah, we specified before.
Because I thought Klee was talking about something like SU10 type.
No.
No.
We clarified this point. No.
Okay.
Okay. So I guess,
Fong made a point that is related to what Ray is saying. So A8 has a quantity of parallel vector classes which is not equal to the quantity of parallel, let's call it edge classes because these are lattices. So we have parallel edge classes in E8 of some quantity, which is 120 to be exact. And then because the 240 root vectors come in antipodal pairs, so but that is not the quantity of parallel edge classes in A8. So what Ray said,
14,
yeah. So what Ray said is true. So the point sets, you're just taking the points, not the edges. So you're taking the lattice as a point set, not the crystal with edges drawn between points. So if you take that point set, translate 2 copies by 90 degrees, you get the exact same point set as E8. But the way you draw the edge connections from near neighbor distances is richer for E8, so you have more parallel vector classes based on how you drew edges. Okay, okay, I get it.
It's when you take the closest neighbor in the global point set, then you rebuild the E8 automatically.
So that's all I wanted to say about this.
Okay.